different breed than your app TikTok.
See, all over the world. Full world was India. I did. একশো জনের বেশি আসতে পারবে না তো। অ্যাক্সিডেন্ট লিমিট আছে ম্যাক্সিমাম 100।
Good evening, everybody. I'm Adinarayan. I'm a third year BTech student at Department of Aerospace Engineering, IIT Madras. And today we'll be having our first weekly session for the School Connect program, part of the Fundamentals of Aerospace. So this program is the lectures for this program are being taken by Professor Bharat Govindrajan and Professor Ranjit Mohan. And the TAs for this course are myself, Adinarayan, and Rakshan. So we'll be starting off today's session with a quick summary. I hope everybody is ready. I would like everybody to just give a thumbs up if things are fine. And yes, that's good. That's good. Let's start. So I'll firstly just summarize whatever we have done as part of this week's lecture. And then there are probably like a quick set of few questions where I guess 4 questions or something where you can just try answering them. And then we can move on to the doubts that you guys have sent. People who have a set of doubts, I request you to please post it on the Google form. Also, I request you guys to be on mute. And yes, so I request all of you to send your doubts on the Google form, as well as if there are any doubts, I can probably take it up during the class as well. So yes, let's get started. And I'd request you to not annotate on the page once again. Can you guys please stop annotating? Yes. So better, you can see your name. So let's not do this. Fine. So let us start off. So firstly, we started this course from classification. So we classified the kinds of aircrafts that we want. We see many things in the air. We see a helicopter, we see an aeroplane going around, we see hot air balloon. So let us just have a basic classification of what these things can fall in, so that we have a better understanding of everything else coming. So anything that's flying is kind of divided into two sections. Okay. One is called the aerostat. Okay. And the other is called the aerodyne. Now, what is an aerostat? Aerostat is flies, something that flies due to the buoyancy of the atmosphere. Due to buoyancy as a property in general. Due to buoyancy. So, for example, hot air balloons. Consider hot air balloons. A simple example. Hot air balloons are basically, balloons, something of this sort, which are, there is some heat that's going on. So the density inside is lower than the density outside of the atmosphere. So say this is density rho one and this is density rho two. So the density inside is lower, and hence there is a push that you get from the air. So there is a push from the air that you get, which pushes you up. So this is the reason why aerostats go above. They go into the atmosphere. They stay in the atmosphere. So what are aerodynes? Aerodynes are basically structures or flight craft which are heavier than air. They are aircraft, or let me not call them aircraft for now. Yeah, they're aircraft which are heavier than air. Now, for example, we know aeroplane is something we are very well aware of. At this point, we see them every day making noises, and all of those. Or so when we get some noise from the atmosphere, we go out, look out, and be like, "Oh, nice! There's a plane flying around." Stuff like that. So there is an aeroplane, and other examples, say a helicopter, which again a distinct noise that we can actually figure out. So if there is a helicopter going around, you can instinctively spot, and you can sense that, yeah, it's a helicopter that's going around. So this aerodyne is further classified into two sections. One is called the air breathing, and the other is a non-air breathing. And this pertains to the kind of propelling system that you deploy in that particular aircraft. By propelling system, I mean something that pushes it forward. So air breathing, as Sir explained, is, for example, a turbojet. A turbojet engine is as an air breathing system. Air breathing. And then the example of a non-air breathing system, say for a rocket. Rocket is a non-air breathing. Say you have a rocket. There's no air that you can carry in the rocket. Fine. So you have your fuel and your oxidizer inside, and there is some reaction happening which takes it up. Now, how this is done is something let us not get into right now. And so I'd like you guys to answer a quick question on the Menti page. I'll just share that as well. Just a second. Mhm. So I'd like you guys to
Excuse me,
go
sir.
answer on the menti.com page. So
Can you please explain non-breathing aircrafts again?
uh okay, sure. 1 second. Oh, can you just try this out? I'll get to that question if you don't mind.
Okay, sir.
So go to menti.com page and use this code, and I'd like you guys to answer this question. So we see quite a few answers right now. But yep, let us understand what exactly an airship. What is an airship? An airship is an aerostat. Okay. Something that is flying because of buoyancy, something that is flying because the atmosphere is pushing it up. Once the atmosphere is pushing it up, there's nothing else that's holding it. So there is no propelling device inside an airship. Right. There's no propelling device inside an airship. Hence, it doesn't fall under air breathing nor a non-air breathing system. It's nothing. Okay, it's you can call it a non-air breathing system, but there's no propelling device itself. That's part of it. So yeah, we can get back to our page.
Excuse me, sir.
Yes.
I have a doubt regarding the assignments.
Sorry, I mean, I'd like you to wait for a while. Then only questions pertaining to the concepts right now would be entertained, and we can get to them towards the end probably. We don't know.
Okay.
Yep. And I'd like you guys to just probably just send a text in the chat,
Excuse me, sir.
mute and ask the question. Yes, there was somebody. Was it Shivan? Right, I'll continue. So the question that Prashant had asked, okay, about what exactly is a turbojet? What exactly is a non-air breathing engine? So air breathing engine is something that, for example, take a turbojet, basically a jet engine. You have a jet engine. I request you guys to mute yourself. So yeah. So you have
headphones.
sorry,
ப்ளூ கலர் இல்ல கேட்காது. உள்ள இருக்கு
excuse me. Can you just mute yourself if you don't mind? Tejaswini. Yep. So let's carry on. So you have an air breathing engine. An air breathing engine is basically something where you take up oxygen from the air around it. Okay. And then there is some process happening inside. There is some combustion reaction happening inside. There's a combustion process which gives a lot of energy. And this energy is pushed back, and which gives you some energy to move forward. And that's what an air breathing engine basically takes up. It takes up air from the surroundings and combusts it, takes oxygen from the surroundings, combusts it. There is a fuel here that we provide. There's a fuel as part of the engine that is given. Okay. And this will give you a propelling behavior towards the front. Now, in a rocket, okay, the issue that you face in a rocket is that rockets are going to fly probably at outside atmosphere. Say this is your Earth. Okay. And then if this is your Earth and you have your atmosphere probably ending somewhere here. Okay. Rocket is going to be somewhere here. Say this is your rocket. Somewhere here. Now, there is no air at all in that region, right? No air in this region. So if there is no air in this region, you don't have anything to take oxygen from, correct? There's nothing to take oxygen from. And hence, you need to carry both. Okay, this rocket is not being able to take air from surroundings, and that is termed as non-air breathing. So basically, systems which can't, for any reason, which can't take up air from the surroundings or oxygen from the surroundings, are termed as non-air breathing systems. I hope that part is clear to somebody who had asked. And yeah.
Yes, sir. Thank you.
Yes. Yeah. Let's go to the next part. Earth and its atmosphere, and that's where we've continued. Okay. So just a second. Yes. Earth and its atmosphere. You have your Earth, the sphere part of it. Okay. And then you have your atmosphere finally ending somewhere here. Right. So you have your atmosphere ending here. And now, in between just the surface of your Earth, surface is here, and then the exit is here. The last point above Earth where you don't find air anymore. That is the end of the atmosphere. So there are multiple regions between the surface and the end point. So, and these regions are classified based on the temperatures and density in that region. So the first one is called the troposphere. Okay, troposphere, which goes up to at 10 kilometers, roughly 10, 12 kilometers. And then you have a stratosphere, and then you have mesosphere, thermosphere, and then exosphere. Exosphere is the last, so this is the end. I'll indicate the end with a pink line, probably. And then this is your exosphere. Now, this defines where you're flying and what kind of air you need. For example, the aircrafts that that fly, the airplanes that we know of, okay, the airplanes that we know of, they're going to fly at probably 10-kilometer altitude. I mean, all of you would have probably, when you go in your plane, when you go in a flight, you hear the pilot saying, we're cruising at 30,000 feet. 30,000 feet is like roughly 10 kilometers as an altitude. Yeah. And this will lie in, between troposphere and stratosphere. So it's somewhere there, and that's where you fly. Now, again, I just want you guys to answer a quick question before we move on to the next part. I hope you can see the question. Before that, yeah, answer this as well. So are you guys able to see this? I hope you're able to look at this. Just give a thumbs up if you don't mind. Guys, please don't annotate on the screen, please.
No gears. Okay.
So, guys, 1 second. Please don't annotate on the screen.
Excuse me, sir.
Yes.
Sir, do we have to take down the notes which are you're writing?
No, it's up to you. I guess you guys would have already gone through the lecture. If you don't mind, you can. It's up to you.
Okay. Or sir, can we get this PDF also on which you're writing?
Sure, I'll let you know. I'm not sure about it. I'll let you know about it. Okay?
Okay.
Yes. So people have answered. And yeah, Aerodyne is, helicopter is an Aerodyne. The other two are basically aerostat systems where, both of them are carried because of the atmosphere, which is, because of the atmosphere which pushes it up. Okay. And let us go to the next bit.
Excuse me, sir.
Yes.
How can we answer to this question?
Sorry. I mean, I guess sorry. So there is this website called menti.com. Okay. menti.com. And then go there and use this code and then answer the question.
Okay,
Is that
sir.
fine? Is that clear?
Okay.
Yes. Sorry. I mean, I think I had fine, but okay. And yes.
Sir, can you say the code once again?
Which code, no? Sir?
For this menti.com.
The use code is written here. It's here. 1 second. I guess you're able to look at my screen.
Okay, sir.
The code is here, 24725013. The one that's here. Is that clear? Yes. Let's move on to another question. Okay, part of the
Sir,
the different layers of the atmosphere.
sir,
Yes,
sir, I need the multimeter code, sir.
it's here, just on top, 24725013. It's on the top of the screen.
Atmosphere, exosphere.
Thank you, sir.
I want you guys to be on mute, please. Everybody. So yes, I guess many have answered right now. So yeah, mesosphere, thermosphere, exosphere is the order. Let me get back to my screen. Yeah. So as I've written here, mesosphere comes first. When you go, when you start off from the Earth, you first see the stratosphere, and then you see the troposphere, and then the stratosphere, and then you go to mesosphere, thermosphere, exosphere. Okay. So on. Next, we look at what we then looked at different kinds of flight vehicles. So we looked at something called launch vehicles, which are part of ISRO, and name of few like SLV, PSLV, GSLV, and so on. And then we have rockets. Rockets are basically things that finally fly off, go out. Different kinds of rockets that have gone. Recently, we saw Chandrayaan that was taken. A rocket is basically something that takes it. Okay, and then we know missiles. Missiles are basically similar to rockets, which can be guided. Okay, which can be guided as well as controlled. So say I want to start as well as control. Say I know my location A. I start from location A and then I want to get to some location B. A missile can be perfectly guided to, kind of go to this point at the required angle that you want. That is a missile. Okay. And then, to do all of this, firstly, rockets and then Earths. Just now I discussed about the, components of the atmosphere. We also have different kinds of orbits. Okay, we have something called, so you have the Earth, and then you have something called a low Earth orbit. Low Earth orbit. And then you have something called a medium Earth orbit. Medium Earth orbit. And then finally you have something called a geosynchronous or a geostationary. Now there is a subtle difference between a geosynchronous and a geostationary orbit. And I'd like to explain that part clearly. But before that, you can just try out a question on the same as posted it. Just a second. So this is the case. Fine. Now, low Earth orbit is roughly from the surface of the Earth. So basically, Earth is starting here, and so from the surface of the Earth, it goes on till above 200 kilometers on top. And then the medium Earth orbit is from 200 kilometers to roughly about 30,000, 35,000 kilometers. Say 35,000 kilometers. 1,000 kilometers. And that's where the medium Earth orbit goes. And then this geostationary orbit is at a radius of approximately 36,000 kilometers. The exact number is not very clear. Yep. So before moving on to the difference between these two, I'd like you guys to try out this question. So try this question. The same code, you can go to menti.com and try it out. People are okay. Are you guys able to access the menti.com page? I hope you're able to access. There are a few people answering the question, but I'd like everybody to participate. People on YouTube as well. Please go to menti.com and submit your answers.
Sir,
Yes.
sir, can you please repeat what's a geostationary orbit?
Yes, I'll come to that. So for people who have gone through the lecture, I just wanted to see whether they're able to answer this question. And once they're done, I'll explain the whole thing. Is that fine?
Yes, sir.
So yeah, let us get to the explanation. So a geostationary orbit is basically an orbit where, or before geostationary orbit, I'll talk about geosynchronous orbit. Geosynchronous. It's basically an orbit where you have your Earth, and wait, let me get a proper circle first. This is your Earth, and then say you're somewhere at this altitude. You have an orbit at this altitude. Okay. So both you, by you I mean the satellite. So the satellite here that's there, okay, that the time period of rotation of the satellite as well as the Earth is the same. That is, so say the satellite starts here at some time. For the satellite to completely go around this orbit and come back to this point will take a time of about 24 hours. That is 1 day on Earth. That is a geosynchronous orbit. So anything that is there on that orbit with a particular speed, which can go at this time period, is a geosynchronous. Is part of a geosynchronous orbit. Okay. Now, my question was: is a geosynchronous orbit a geostationary orbit? Okay. The difference between a geosynchronous and a geostationary orbit is as follows. A geostationary orbit is a geosynchronous orbit. So what is a geostationary orbit? Let us get to the same thing. What is a geostationary orbit? So a geostationary orbit is that where, okay, this is the same setup. You have the orbit, the satellite is here. Okay. And then
Sir?
here I'm standing here. Yes?
Sir, can you be little louder?
Okay, are you not able to hear?
Yes, sir. Little louder, sir, please.
Sure. Okay, fine. Is this clear now?
Now okay, sir.
Okay, fine. Yes, I'll be louder. Yes. So consider this, say this is your satellite. This is the satellite that's there. And it is part of a geosynchronous orbit. What does it imply? It means that it takes a time of 24 hours for 1 day to completely go around this path, to completely go around this orbit. It takes 24 hours. Okay. Now, in the meantime, my Earth will also rotate, correct? The Earth will also rotate about its own axis. So I will also be going around the Earth. In a geostationary orbit, that is, if a satellite is part of a geostationary orbit, say after some time, we start off here, both myself and the satellite, we start off here. At some time t later, okay, I will be somewhere here. And the satellite is going to be somewhere here. Okay. So at any time that I see, I just look above and I look at the sky, and then somehow I'm able to see the satellite. Yeah, we need a telescope. Assume that somehow you're able to see a satellite. Okay. Any time of the day, you will be able to see the satellite at the same location. And such an orbit where the satellite exists is called a geostationary satellite. This is called a geostationary satellite. Right. Now, the specific difference. I request you guys to not annotate on this, please. Yeah. So, for a geostationary satellite, say this is your Earth. Okay. This is your Earth, and this is your equator. Equator of your Earth. Now, for a geostationary orbit, okay, for a geostationary satellite, it is going to be part of this orbit where it aligns with the equator. Something that aligns with the equator. Such that, see, your Earth is this way, right? Your Earth is going to spin this way. Your Earth is going to rotate this way. Now, if you're here, if the satellite is here and you're here somewhere here on the Earth, the satellite is on the in the orbit. Right? So as the Earth rotates, so say this is my Earth, and then this is the satellite. So as the satellite rotates, as the satellite goes in its path, the Earth is as well rotating. So in that situation, both of them, are part of the same line. There's nothing changing. Both of them, you can, like, for example, if I am the person and I'm trying to look at the satellite, I'll be seeing the same satellite at every time instant that I wish to see. Yeah. Whereas in a geosynchronous orbit, in a very general sense, is where you have the uh, Earth here, and this is your equator here. Now the time period, that is the time taken by you to revolve around the Earth, basically as part of the orbit, depends on how far you are from the Earth. Depends on how far you are from the Earth, which is basically the radius. So say the orbit is somewhere here. A geosynchronous orbit is basically at some radius, which is 36,000 kilometers. Okay. Now I can pick any orbit at 36,000 kilometers. I need not always go around, I need not go around this equator. My path need not be aligned with the equator. That is not necessary. I can choose to pick a shape which is something like this. I'll decide to go this way. What if I do this? Now, as Earth rotates, my Earth is here. I say this is a point on the Earth, and then this is rotating. But my point is going this way. My satellite is going this way, whereas Earth is rotating this way. So when you're standing here, you can see that the satellite is moving in space. The Earth is rotating this way, whereas this satellite is going this way. And that, in general, is a geosynchronous orbit. This is a geosynchronous orbit. So all geosynchronous orbits are not geostationary orbits. A geostationary orbit is a geosynchronous orbit. Orbit is a geosynchronous orbit.
Excuse me.
One. Sorry. I hope this part is clear. Did you guys understand this? I'd like you to
Hello, Bonna.
react thumbs up. I'd like you to react with thumbs up if things are clear.
So can you give some definition for the both?
I mean, there is no specific definition per se. Okay, I think you have to probably understand what is going on. That's more easier to explain.
Excuse me. So in a geosynchronous orbit, is it necessary for it to be opposite to the orbit aligned with the equator?
No,
Or could
it's
it be
not necessary.
any-
My point is it can be any orbit. It can even be the orbit which is aligned with the equator. Okay. One of the geosynchronous orbits is the geostationary orbit.
Can you again explain about the
okay, I
geostationary
got it.
orbit?
Sorry, I hope
Understood.
that
Thank
part
you.
is clear. Yeah, okay. And I'd like you guys to stop meditating on the board, please. And sorry, there was another question. What was the question? Fine, I'll continue then. Yes. And then the last lecture was on forces on an airplane, and then the first thing that we did was we considered an airplane. We took an airplane, okay, and then which is something like this, right? And say it's right now it's on the runway. Fine. So starting with some speed 0, and then it goes off to some speed and takes it. Now, when the first force that we really know of about the airplane, whether or not we know about anything else, is the weight. We know that the airplane is going to have a weight, right? So there is going to be a W that is going to act downward. Okay. And then since the airplane has an engine, okay, it is going to produce a thrust. Okay. It's going to propel it forward, it's going to push it forward. Okay. And in the process, as I go faster and faster in the atmosphere, in the air, I'm going to face a drag. Okay. And this is what Sir explained, and he said, drag will depend on the density, that is, how dense the atmosphere is around you, density. I request you guys to stop annotating, please.
Could
And
you explain this point again?
which point, sir?
The drag one that you were talking
Yeah,
about
yeah,
right
sure.
now.
I'll explain that. The drag is basically some force that you feel when you're going through a medium. Okay. I request you to stop annotating on the board, please. This is kind of disturbing to the class as well. So yeah, the drag is basically the force that you feel when you're moving through a fluid medium. Say, for example, you have a bucket of water. I mean, you can go try this experiment. Say you have a bucket of water. Okay, and then you put your hand into the bucket of water, and then you try moving your hand. Okay, you feel a larger. Same with people. I mean, people, guys who have tried swimming. Okay, you go to the pool. Hello, yes.
Sir, I have a doubt, sir.
One second.
Sir,
I mean, I request you wait for a while before we finish. Just a second. I'll finish the summary and then we can get to the doubt. Okay. Yes. So say you have a bucket of water and then you move. Sorry, I finished this. So say you're in a swimming pool. People who tried swimming, have experience, would have experienced this for sure. You swim and then it's more difficult. It's easier to walk, on earth rather than swim inside water. That's because there is some force that you feel from the water, which is drag. Trying to go forward, but the water is pushing you back. And similarly, for an airplane as well. The reason we don't, like, for example, when we are walking around, okay, we don't feel a large force from air because we are walking at very, very low speed. But then say, there is one, huge, hurricane or tsunami or something where, there is, or say there are floods that happen. And then there is heavy wind all around, there's huge breeze. And then there are, at times you go stand out and then the wind is, or the breeze is pushing you back. Okay. So a force is a drag. Okay. Something that the surrounding atmosphere forces on you. Okay. So that is a drag. Okay. And this drag depends on the density of the atmosphere. Density of the atmosphere rho. Okay. And then it depends on the speed at which you're going. The faster you go, you feel huge force. You can, I mean, all of what I'm saying, you can try it with a bucket of water. You take a bucket of water, move your hand through it. Okay. The faster you go, you'll feel a larger force. Okay. And it also finally depends on projected area. Projected area. And this projected area is S. And how did we define this projected area? So say you have a ball. Okay. And then there is a wall behind, a screen behind, and then you shine light on this. Okay. And there will be some part which creates a shadow behind. And the area of this shadow, the area of the shape of the shadow is the projected area. So you can have different sorts of projected area. For a ball, it will kind of look like a circle. And then for an aeroplane, you can see, for example, say I have an aeroplane. Okay. The projected area will probably look something like this. You have two wings, and then the tail, and then you have two engines here. This will be the projected area for an airplane. Okay. And then we further went on and we defined this d to be CD times rho v square times s. And really doesn't matter as to why this mathematics is important. Right? We don't want to get into this math behind, but we do know that as we go faster and faster, we face more and more force from the atmosphere. And on a similar basis, you also have a lift. See, finally we want to fly up. Okay, and we want to fly. And to fly, we need to first get off Earth. To get off Earth, we need a force that will, take you up. And that is the lift. So at an instant when, the lift, say this is your weight acting, your weight is going to act always. Okay. So as you go faster and faster, your lift should keep increasing. To such an extent where it overcomes all the weight that you have and then it finally lift. Okay. And that is called your lift. And the lift again depends similarly, and it's depends on V, S, and rho again. And the faster you go, the more lift you generate. And that is the reason where you need a runway. You have a runway and then you have a flight. Okay. And then it goes faster and faster, and at some point, your lift will start becoming more than your weight, and then you lift off. And that's it. And by the time you also have a huge drag that you're facing. So you need to speed up really well for you to lift off the surface. And similarly, when we are coming to land, okay, when you're coming to land, you need to stop. You're at a really, really high speed. And you need to stop. And that is where you'll make use of the drag. You'll stop your engines mostly. Stop your engines, and then you'll be like, yeah, fine. Let the air push me as much as possible. So that if this is the end of the runway, I stop somewhere. And that's what I want. So I need to slow down in this case. Right? And yes, I need to slow down here. And finally, the drag helps in doing this. You need to slow down to come to a still. And yeah, I guess these were the topics majorly covered as part of this week's lecture. And yeah, I guess now we can probably get to the doubts that you have. So I'd request you guys to raise your hands before going through doubts. Okay, Vashish V.
Yes, sir. Could you hear me?
Yes.
Yeah. So could you please repeat the last point where you said you'll need drag to slow down? So the landing part, I believe. Could you please repeat it?
Fine. Yes. See. So you're coming up. Okay, you understand this point, right? When you're landing, okay, you're coming down with a really high speed. You agree? The speed is very, very high. You're coming down with a really high speed, and then you have to touch down to the surface. Yeah, you have to touch down to the surface first here. You have to touch down to the surface where your wheels touch the ground. That's the touchdown. Okay, and then as you go ahead, you apply brakes as well. Okay, and in the process of your brakes cannot completely stop you. Okay, you are at a really, really high speed. Okay, so you also need the help of air to push you back. So say there is air here. Air is pushing you back, which is technically the drag that you're facing. It is the air push that you get. So yeah, I guess is that your doubt? I hope that is clear. Vashish? Okay, I'll move on to the next person. Tarun?
Hello, sir. I
Yes.
have a doubt.
Hello. Yep.
So in the graded assignment,
Hmm.
they were given some questions about stall. What is stall, sir?
Wait, I think there's a lot more time to come to that. It's part of next week's syllabus, I guess. Let us not jump the guns right now. Let us go slowly and figure out stuff.
Okay, sir.
You will get it clarified when you do it next week.
Okay, sir. Thanks.
Shubham. Also, I request you guys to post your doubts on the Google form as well. There was a form sent to you guys, I suppose. Okay, there are a few questions on that. 1 second.
Sir, so my doubt is, in the first lecture you had mentioned that it would be most efficient to use helicopters as staying airborne in one place. What about in a military point of view, technologies like VTOL and thrust vectoring? Won't that be better because we could speed up faster and we could reach various places faster?
Oh, wait. 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 No, higher scaled up versions and more advanced versions of a helicopter. So helicopter is the starting point, basically. I hope that was clear. And then next is Vayun. before I move on to the other questions in the meeting, let me just clarify a few questions that came on the Google form list. So there's this one question where a person says we know that thrust equals drag. So in one of the cases where sir mentioned that at a steady level flight, steady flight basically, so we're not just cruising, and then in that case you have thrust that's acting forwards, and then there is a drag that's acting behind. And then sir mentioned that thrust should be equal to that. So the question that he's asked is, because we need to move the airplane forward, since the airplane has to move forward, okay, it has to go ahead. Shouldn't thrust be greater than that? Shouldn't thrust be greater than drag? That's the question. Now, yeah, this is a confusion that I'd like to clear. So, consider you have a box. Okay, let us get to Newton's law. You have a box which is on a surface. Say it is at rest with 0 meters per second. Okay, and then you have a force F acting this way, and then the force F acting this way. The net force on this object is 0, right? There is a force coming this way, there is another force coming this way. There's nothing happening. So the net force is 0, and then the acceleration provided by this force configuration is 0. Okay. Now, in this case, the object is at rest. Okay, is at 0 meters per second speed. It's not moving, and then the acceleration is also not 0. There's nothing that is pushing it forward or anything. It will stay there. But consider an example where I have the same block, and then I apply same two forces F, and then there is a speed that it initially has. Okay. Now this force configuration again will not produce an acceleration. The acceleration is going to be 0. The net force is 0. F net is 0. Okay. But the F net being 0, the net force being 0 for that matter, is not going to affect the speed here, right? This will still move forward with the speed of 5 meters per second. The speed is not being affected by this, 0 net force acting on the body. So the object will definitely move forward. Say for example in a delta t of 1 second, the object will move forward by 5 meters, and that will keep happening. So even if thrust is equal to drag, okay, the airplane will be having a velocity. Okay, there will be a v, and the airplane will move forward. So I hope this clarifies that question. And there was another question. Okay. So there is one question. It's asked, why is it more difficult to fly a rocket or a launch vehicle than an airplane, even though the drag would be very less, considering that the density is low at outer space? Okay. They are completely different problems, to be specific. Okay. An airplane is something that should be still, and it should be able to cruise at that high altitude for a long time. Okay, you can't suddenly have an airplane falling off or going up or something. You need it to be there. So that itself is difficult. I'm not saying that it's not difficult, but the part of the question which makes it interesting is, would the outer atmosphere has very low air molecules. Okay, and the density is less. Okay, but the problem here is that for you to escape Earth, okay, that is basically for you to escape the gravitational pull of Earth. Is, guys, I request you to please stop annotating on the page. So say there is Earth, okay, the Earth is going to pull you down. The Earth is pulling you down, and in the case of a rocket, okay, the rocket has to go out of Earth's atmosphere. Okay, That means it has to actually, move out of Earth's gravitational force completely. And that requires very, very high, energy. Very high energy to exit Earth's gravitational field. Earth's gravitational field. So I hope that answers question. Whereas in the case of an airplane, you're not wanting to, go out. So there are a different set of problems with an airplane, but yeah, pertaining to your question, I guess I hope I've answered it. And yeah, there's one more question which says, I think that
Sir,
shouldn't
can
be.
you explain about the geosynchronous orbit?
Yeah, give me 1 second. Okay, the factor of 2. I mean, I hope you guys. Okay, don't worry about the formula that we're using for drag right now. I don't think that's any major concern. We'll get back to it slowly. So as we go ahead in this course, we'll probably use more better versions of the drag formula. Okay, so don't worry about the formula for now. And yes, we'll get back to the questions in class right now. There was somebody who asked about geosynchronous satellite and geosynchronous orbit. The geosynchronous orbit is that set of orbits, okay, at some radius r, okay, where your time period of revolution around Earth, the time period of revolution.
Excuse me, sir.
1 second. Yes. I request others to mute yourselves. And please stop annotating on the board. I mean, it's kind of disturbing to everybody.
Sir, I have a doubt, sir.
Yes.
Sir, probably in space there will be no air, no, sir.
1 second, sorry. Is this pertaining to the previous question?
Sir, probably in space there will be no air, no, sir.
Yes.
So how can you make drag there so that you can stop something?
We don't want to stop something. Exactly. So that's another problem. Okay. We won't be able to stop anything with drag. That's a good question. Okay. If you go into atmosphere.
Slowing down spacecrafts, airships.
Yeah, exactly. They have a different set of controls altogether. Okay. Say you have a rocket. Okay. A rocket is slowed down and speeded up based on its thrust itself. So I mean, I don't want to bring up new terms right now, but they have certain systems. Let us not get very deep into it, but there are a few control systems. So say there is, okay, I'll give you a very easy picture to this. You have a rocket. Guys, please don't annotate on the board. It's quite disturbing. I hope you guys stop doing that. And yeah, so say you have a rocket, okay, and then there is some amount of, there is some air that it pushes out, correct? Now, based on what do I say? The rate at which you push this air down, you can control the speed of the airplane in a rough sense. Okay, let us not get into very details of this, but yeah, based on how fast you're pushing it out, you can control the speed, and that will kind of help you slow it down as well. And you can also there are other mechanisms which I don't want to get into right now, but yeah, you can definitely slow down with most of these. There are different control systems built into it, which will help you do. I hope that part was clear. Yes. And yes. For this, the geosynchronous, somebody asked, I'll explain it for.
Hello, sir.
1 second.
Hello.
1 second, please.
Okay, sir. Thank you.
So time period of revolution over a geosynchronous revolution in a geosynchronous orbit is 24 hours. Okay, that is 1 day. Any such orbit where you are on Earth, I mean on top of Earth, is a geosynchronous orbit. Okay. Now that orbit can, be aligned with the equator. That is, say you have the Earth, and then you have the equator. The orbit can be along the equator. That is, far away, but on the same circle. It's basically a concentric circle to the equator. So that is a geostationary orbit, which is a sub, what do I say? It's an example of a geosynchronous orbit, the geostationary orbit. And every other orbit that you get is, including this, is a geosynchronous orbit. So you can even, orbit the Earth this way. There's nothing wrong in doing it. Our systems, our rockets, we can fly it however we want. Okay. So you can even fly a satellite in that orientation as well. And that is another geosynchronous orbit, but it is not a geostationary orbit. I hope that part was clear. And yeah, next question. Okay, I request you guys to raise your hand for have a look at it. Vayun Nambudri.
Am I audible, sir?
Yes.
With regards to this geosynchronous orbit, is it perhaps like the periapsis and the apoapsis would be equal?
For wait. Sorry, I didn't get your question. Can you repeat your question?
Well, in a geosynchronous orbit, is it necessary for the periapsis and the apoapsis to be equal at all times?
Need not be.
So it could be like a pretty tilted one also.
Yeah, it can be. Yes.
And one
You
more
have to just
question
make sure
was.
that the time period is the same. That's all.
Oh, okay. And one more question was that another person had mentioned about something like a brake system for rockets. So could we consider RCS as a brake system?
Can you just sorry, one second. Can you repeat your question? I'm really sorry.
Well, one person just previously mentioned something like a brake system for rockets. So could we say RCS as a measure?
What do you mean by RCS? I mean, I'd like you to.
I pretty much don't remember the full form.
Okay.
1 second. Okay, I'll get back to you later.
Yeah, sure. No issues. As far as I know, the kind of systems that, I mean, probably, I guess the example that you're trying to give is something that on Earth where, you make use of friction as well. The friction is helping you stop. Whereas there is nothing, there's no friction, there's no air, in the atmosphere. So, I mean, out of atmosphere, in space. So you can't, in most cases, you won't be able to use, but yeah, I'd want you to get back in that question. And next, Putra. Please stop annotating on the screen.
Sir, could you please provide us some related to that payload and the launch vehicle density?
Sorry?
Could you please provide us problems related to that payload and launch vehicle?
Okay, right now this is not more into problems, so let us do that later. Okay. For now, it's more of it's more about you guys getting an idea of what exactly they are. Okay, we will be solving problems as we go later. So right now, let's not worry about. Let us just have an intuitive understanding.
Okay, sir. One more question. In the graded assignment, they
Second,
have
sorry.
been
I mean, if people continue annotating on board, I mean, I guess I might have to stop them doing it. It's kind of disturbing for everybody on screen. So please stop annotating.
Sir,
Yes.
one more question. Could you please tell about the question that has been asked in the graded assignment in the concept of cylindrical part in which the air molecules would move?
That is part of the next week's lecture. I think we'll get back to it next week. Let us focus on questions that are part of week 1 lectures, so that everybody is on the same page before we move to week 2.
Okay, sir. Thank you, sir.
And next is Pranesh. Pranishka. Vartika?
Yeah, this is Kanishka.
Yes.
Is it possible to design a system where it conquers both lift and drag?
Sorry, I mean, your voice is breaking. Can you repeat your question again?
Yes, sir. Can you hear me now?
Yes, I can hear you.
Is it possible to design a system which can overcome both weight and drag? I know it is not possible now, but
Systems, right?
will it be possible in the future?
I didn't quite get your question. Like, for example, take an aeroplane. It is overcoming the lift, overcoming your weight, and it is also overcoming the drag, right? I mean, I hope, was that your question?
Yes, sir.
So, I mean, there are
Yes, sir.
systems right
Both
now
at the
doing that, right?
same time.
There are systems
Oh,
doing that.
I'm not aware of that.
No, I mean, okay. See, an aeroplane is something that is lifting and as well as going ahead. Correct. So it is overcoming your weight and as well as overcoming the drag to be faster.
No, sir. I mean, propellers, they reduce the drag, and then we have wings to get, to provide lift. What if we combine both and overcome both of them, drag and weight?
Oh, you're saying you want a single system which can do both instead of a wing and an engine doing it separately. Is that your question? See, it's kind of similar here. The first person, like, I mean, as Sir mentioned in his lecture, George Cayley is that person who, George Cayley, said that, it's easier to come up with a system that can fly as well as propel if the lifting component and the component that produces propulsion are separated. Like, for example, if you consider a bird does both together. Okay. It propels as well as, lifts with the same system. It does it with the wing. Okay. Whereas he realized that, it's difficult to do this for a mechanical system that we want to come up with. And he said, let's separate them and it will make it easier. So sometime later, people are working on flapping wings as well, which, if it goes well in future, we can have something that does both. Right? I hope that answers the question. And guys, I mean, I kind of getting annoying right now. You guys are, annotating completely on the screen, disturbing everybody at this point. Okay. Right. Okay, next, Shivansh. Shivansh, are you there? Oh, 1 second.
Yes, sir. Sir.
Yes.
Sir, actually, I wanted to ask, how can we access our assignments or practice sheets?
I'm not sure about it. I guess the team will get back to you on the same. I'm not, I mean, right now I'm not handling that. We'll just mail.
Sir, one more thing. Actually, I wanted to ask, can you told me to
जो
that
करना मतलब
you will answer at the last of the class that can we get the PDF of both the lectures which were discussed?
Okay, which two lectures are you talking about, sir?
Sir, the first one and the second.
The lectures by Professor Bharat?
Sir, yes, sir. Before
Okay, wait, are there
today's
any
lecture.
PDFs to it?
Sir, I don't know. That's why I was asking that.
Okay, I'm not
can
sure.
we get
I'll
it?
confirm. I'll confirm with them and I'll get back to you. Okay, I'm not sure whether we can share them right now, but I'll confirm and I'll get back.
Okay, sir.
Sir, I have a doubt, sir.
1 second. I mean, I request you guys to be please be on
Sir, you
mute.
called me earlier. I was unable to unmute. So can I ask you
Yeah,
again?
and I request you guys to stop annotating at this point. It's just annoying.
Sir, I was unable to unmute earlier when you called out my name. I'm Pranesh, sir. Can I ask my question?
Your
Yeah,
voice is
okay.
not clear, sir.
One second. Ganesh, please be on mute. Please be on mute.
Sir, your voice.
Yes, sir.
Yes. Ganesh, yes. What's your question?
Can you please clear your voice, sir?
Is my voice clear? I hope my voice is clear.
Sir, can you hear me?
Yes, I can hear you. Yes, Ganesh.
Sir, as for the assignments provided, does
Can
it after we watch week 1 and week 2 videos, after that only we are supposed to attempt
Yes.
the graded assignment, right, sir?
Yes. Yes.
Okay, sir. Thank you.
Yes. And Vartika?
Sir, I have a doubt.
Am I audible, Vartika?
Yes.
So I wanted to ask a doubt. So basically, in the first week lectures, we were told about takeoff weight and plane's weight. There was a relation told between them. I couldn't understand the relation and the numericals also.
Wait, there are no numericals to it, right? In the first week's lecture.
No, like the takeoff's weight is much more than the plane's weight. There was some relation told.
Okay, there was no relation. Okay, fine. You're talking about the rocket case, right? Where there was a payload weight and then there was a takeoff weight.
Yes,
Correct.
sir.
Okay. So payload is basically something that is part of the mission. Say you're, for example, taking a rocket. Okay. And then the rocket is carrying some rover that you want to drop on Mars. Okay. And that is going to collect and give you information back to Earth about Mars. Okay. Now, the payload in this case is the rover. Okay. The rover is what is being taken, and that is what is important for you. So the weight of the payload is basically the weight of the rover. Now, to achieve this mission, okay, you need a rocket, you need a fuel system, you need to take this all above. You need to take it to Mars. So every other weight, including the payload weight, is the total takeoff weight. Basically, the weight of the system before you take off is the takeoff weight. So that will always be more than the payload weight because you have multiple other systems that is helping you to go out of Earth first.
I don't show to मेरी class में.
I hope that part is clear. Okay.
Sir, I have a doubt.
1 second. I mean, I request you guys to raise hand. I'm calling you. Okay. Yes, Kishore, continue.
Sir, for geostationary object, you told it takes 1 day for complete revolution around the Earth, no, sir? So then it could travel at the speed of same. It could travel along the speed of the Earth, same speed, sir.
See, if you're on Earth, okay, okay, that's a good question. Give me a second. Okay. So, guys, can you please remove your annotations? I hope people who are doing it understand the issue. So, 1 second. Just give me 1 second.
Sir, I have a doubt.
1 second. I'll get back to you. There was one question asked. There was a question about geostationary satellite. I'll just answer that. So basically, a geostationary satellite. Okay, your question was if you're at the same speed as Earth. Okay, you're farther away. So if you're at the same speed, this is going to travel much more in a curved sense than this. Okay, so this will go farther on that arc. So basically, say, 1 second, I'm trying to remove these annotations, and I don't know.
Sir, it's okay, sir. You can say it.
Oh, okay, fine. I'll just better show. I hope you're able to see this. So say you are here. Okay. You are here. This is your Earth's orbit, Earth's surface. Okay. And this is your larger orbit. That is your geostationary orbit. Okay. Now, if both the Earth, like for example, the satellite here is traveling with the same speed as that of the Earth, same speed say V. Okay. And you here are also going
Hello,
to
sir. I had doubts, sir.
one second. There's a question that I'm clearing up right now. Let me get back to this. And so yeah. So say this goes faster with V. Okay, I'm sorry, with the same speed V. Okay. Now, say in time t. In time t, I'm going to cover a distance V delta t. Sorry, Vt. That is going to be the distance that I'm going to cover. This will be Vt here. This distance. Okay. And if I cover this, I'm going to cover the same distance here as well. But for the same distance covered on Earth's surface, I'll be at a larger angle here. Is that clear intuitively? The same Vt, but it's at a larger angle. Okay. Because you're traveling with the same speed. And hence, now if you look up, you can't see the satellite. That means it's not geostationary. So it can't go with Earth's speed for it to be geostationary. I hope that was clear.
Sir, I'm Chandrasekhar, sir. I can ask my doubt.
Yes.
Sir, I have a doubt. The satellite in geostationary, they are continuous act of gravitational force, sir. Is there any another satellite to give a force to continuous to in orbit?
No, it'll okay. Um,
How it can be in stationary, sir, in
yeah,
orbit?
I'm just See, it is stationary with respect to you. Okay, like for example, think of it this way: there is a person beside you. Okay, there is a person standing beside you. He's standing beside you. Okay, you look at him; he's not going anywhere. Correct? Now, but the Earth itself is rotating, and both of you are going together.
Oh, okay, sir.
Both are rotating, but with respect to you, he's stationary. It's like saying, say you and your friend, you both are going in a car. Okay, the car is going. Okay, you are going forward. Your friend is also going forward, but both of you are sitting in the car. Correct. You look at your friend; he's just sitting there. With respect from your view, if you don't see anything around, you don't see the road, you don't see anything. You just see your friend. Your friend is stationary. He's just sitting there. And the relative view is what matters. So relative to you on Earth, the satellite there is stationary. But in reality, the satellite is also rotating. You two are rotating. I hope that was clear.
Okay, sir. Sir, and then what the gravitational force acts on, sir? And the gravitational force attracts means how it can be a stationary, sir, in orbit.
Okay, fine. See, the thing is, okay, just to clarify, which class are you in? So that, I'll just be clear on what I'm explaining.
I'm 12.
You're 12. Okay, fine. So, you would have done this circular motion, right?
Yes, sir.
Yes. So, what is the first thing in a circular motion? You have an object which is in circular motion, uniform circular motion, and then the velocity is always going to be tangential to the arc. Correct? So at this point, the velocity is going to be this way. At this point, the velocity is going to be this way. Correct?
Yes, sir.
Now, all of this is because it's a uniform circular motion. It is going to have a constant radius of turn. Correct? It's going to be r. Right? Now, we know that the centripetal acceleration, there should be some centripetal acceleration which can help achieve this. Correct? And the centripetal acceleration is given by mv square by r. Correct?
Oh, okay, sir. I can understand.
And this is given by the gravitational force.
Sir, and another doubt, sir. One single doubt.
Yes.
Why do the rockets are launched straight up instead of angle, sir? What are the basic difference between a rocket and plane?
See, a plane is the most important thing for a plane. It has to go from a particular point on Earth to the other point on Earth. So you want that to happen. Okay. And a plane is launched at an angle not because that it is more because you want a lift to be produced from the wing. Okay. And that needs a speed and that needs an angle. And this is something I think you will learn as you go ahead in this course. I don't want to go off in too detail right now. Okay, but in the next coming few lectures, sir will explain as to why you need to go at a particular speed for you to lift off. Whereas for a
Okay, sir.
rocket, the most crucial thing is for you to escape the Earth first. Okay, so you need to go above. And say, you just launch a rocket at a wrong angle. Okay, and then it fails. It can fall off anywhere. Okay, and it's not safe as well. So there are multiple aspects to it. I'm just giving a very simple example. Okay, but yeah, it's more important for you to escape the Earth. It doesn't escape the Earth straight again. It goes to an altitude and then follows a trajectory. It follows an orbit and then leaves the Earth. I hope it was clear.
Okay, sir. Thank you, sir.
Yes, guys, I request you to please be on mute. I mean, it's kind of. 1 second, please. Next. Okay, Vayun says, and talk about this. Yeah, who is it?
Hello, sir. I have a doubt.
Yes, Ganesh. Yes. Yes, Ganesh. Yes, Ganesh. Continue.
Sir.
Ganesh, I request you to type it out on the chat. I'll view your message on chat. I mean, there's a lot of background noise.
What is the timing of the
class? Yeah, I mean, 10 more minutes, I guess, will be. I just want to finish off a few more questions from others before I close.
Sir,
But yeah, I mean, yes, Uttara.
sir, exosphere is very hot and warm, and it has
Yes.
very high temperature, right?
Hmm.
Then why space is considered to be very cool?
Hey, that actually depends. That's a good question. Wait, I'll just be clear before I confirm. It is kind of, how do I put this?
The atmosphere.
See, the atmosphere is kind of, there are molecules. Okay, right. Let me not do this now. I'll get back to you properly on this. Let me not do this now. Okay, but it's a good question. I'll get back to your question.
Thank you, sir.
Yes. Any other question?
Am I audible, sir?
Yes.
Good evening, sir.
Yes. Good evening.
What happen if a plane is struck by lightning?
Okay. It's a good question. Now, if you know, planes are made up of conductor. Okay, most of the planes right now, most of them are made up of aluminum sheets. The body is made up of aluminum, and the body is made up of aluminum. The wings are made up of aluminum in most cases. Not all of the current aircraft, but in most cases. Yes. Now, because this is a good conductor, okay, the lighting that comes from top is just taken by the conductor. It's send it down and then is sent back to the ground. So nothing comes inside the body. So there's nothing that affects you sitting inside. I hope that answers your question.
Yes. Thank you, sir. One more question.
Yes.
What happen if bird hits plane? Plane engines damage or not?
It will get damaged. Okay, it can get damaged. I won't say it will. Can get damaged. In those cases, there is also another engine which is made use of to navigate and go forward.
Yeah. Thank you, sir.
Yes. No worries. Next, Nikhil Reddy.
Sir.
Yes.
This is Nikhil Reddy, sir.
Yes.
I have doubts.
Yes.
Sir, can an aeroplane be non-air breathing and move at higher altitudes like mesosphere or thermosphere?
Yes. Those are basically your spaceship. Looks like an aeroplane which can go that high. See, technically all of non-air breathing is considered rocket, but it looks a spaceship looks like an aeroplane which is non-air breathing.
Yes, sir. Thanks, sir.
Yes.
Sir, am I audible?
Yes, you're audible. There is a lot of background noise from somebody. 1 second. Give me 1 second. Okay. Fine. Now, okay. Next doubt, I'll go to Milan Ram. Okay. Yes. You can unmute yourself. Yes.
So, what does mean by cryogenic propulsion? Like, what's the difference between liquid fuel and cryogenic fuel?
See, cryogenic is basically a combination of, all, what do I say? The combination of, a solid, liquid. It's a different kind of a fuel altogether. You can't call it a liquid or a solid in the first place. Okay. It's a very specific kind of a material that is used. Very low temperature gases, stuff like that. I hope that was clear. And next is Mustafa.
Am I audible, sir?
Yes.
So, could you tell the difference between missile and a rocket?
Yeah, missile is basically something which has very advanced guidance and control system. Okay, it can navigate itself correctly wherever necessary to go land and attack or place something at that position. So it has a very good control system compared to a rocket. Rockets too have guidance systems, but it's more advanced in the case of the missile.
Oh, okay, sir. So one more down.
Yes.
Sir, an aeroplane is made of heavy metal, but so while taking the plane airborne, while taking it into the air, while taking off, how do we exactly lift the plane from the ground to the air?
That is what you'll be doing as part of the next week's lecture. So just your enthusiasm is appreciated. You'll be watching that next week.
Got it. Thank you.
Yes. Next, Rohan Gopinath.
Yes, am I audible, sir?
Yes.
So I just want to clarify, geosynchronous is basically an orbit with a radius fixed, but not a fixed axis. And
Not a
geostationary,
fixed. Not a fixed axis.
yeah,
Correct.
and geostationary is the radius fixed and the axis aligned with the Earth's equator. Am I correct?
True. Yes.
All right.
Yeah.
Thank you, sir.
Yeah. No issue. And Rasida.
Sir, am I audible, sir?
Yes.
So, what would happen if the orbital period of a satellite is less than 24 hours, sir?
Nothing will happen. It'll fly at its own orbital period. That's all. It'll fly. It'll fly slower than the rate at which the angle changes will be slower. That's all. There's nothing else that is going to happen at the same orbit. Like for example, if I'm at the orbit, see a particular orbit decides the speed at which you're going. Okay, if you want to stay at that orbit, there is a particular speed at which you have to be going. Geostationary orbit is one orbit where the speed is 1 day. You can have orbits where the speed is not 24 hours, something which is greater than 24 hours, and something that is less than 24 hours. So you can have such orbits. I hope that was clear. And next, Andrew Richard.
Good evening, sir.
Yes, good evening.
So, what is the difference between a missile and a rocket?
I just explained it. It's okay. Missile is basically something which has advanced control system. It is more advanced in its guidance controls and all that. Basically, it can guide itself really well between 2 points. I don't want to go deeper into this right now, but I think that's the broader classification that we can think of. And Nitya.
Sir, I just have a doubt. Can you
Yes.
once again tell me why shouldn't a rocket fly like a aeroplane, like in a tilted way?
See, there's nothing wrong. Like for example, if you consider spaceship, okay, spaceships can be launched this way or this way. But it's more important for you to gain speed as well. Okay. If you if you're able to use all the thrust that you have to actually go up vertically, that is more useful than going horizontally. That's probably one explanation. The other explanation is, say something fails and then you're horizontal. If you're vertical and if something fails, it'll come back and fall there. So you have all safety measures there. But you say you launch horizontally, okay, and then after some time it fails. Now it is going to go fall off somewhere. You don't want some nearby area to get affected because of a mistake. You can probably, that is one of the reasons why such things happen. I hope that was clear. And next, I guess we are done. Rohan Gopinath has asked one question. Would an object or a satellite increase its velocity when flying closer to the Earth? I think, once again, I have to just do the math. Based on speed, no, it depends on, one second. It will be clear before I answer this question. Flying closer to the Earth. Yeah, your speed will be higher. Correct. You're right. Closer to the Earth, you'll be flying faster. If you have to stick to the orbit. And yes, Chandrasekhar, 1 second. Yep.
Sir, sorry for inconvenience, sir.
No,
Can
no,
you
no.
explain that the ratio 1:100, the payload of the rocket?
There is no ratio to it. I mean, as far as I know, there was no ratio. See, what sir wanted to explain was, in a rocket, okay, whatever is your main component that you want to take, okay, say your payload, the payload's weight is going to be very less compared to everything that you're carrying to take the payload there. Okay, you have a very big rocket, you have 3 engines. Okay, now to give a very simple example, say you want to deliver a newspaper, okay, to somebody, and then you take a whole car. You take your car, you go to their house, you go deliver the newspaper. Okay. The payload that you're actually, the payload that is actually part of this example is your newspaper. Newspaper is nothing. The weight of the newspaper is nothing in comparison to the weight of the car. So you're using a very big car with huge weight to go deliver the paper. Okay. And that is the same idea behind, the payload and the takeoff weight for a rocket. The rocket is very, very huge, massive, and has large weight. And then that is going to carry some payload which is of very lower weight. So we need to reduce this ratio. We need to make sure that as much as possible we don't take a lot of weight. It's going to waste more and more fuel in the process of taking it up. I hope that was clear to me.
Yes, sir, clear, sir. Sir, but in assignment there is a question, sir.
Yes.
What is the ratio? That answer is 1:100. So you can explain in mathematical, sir.
Okay, I don't know the question. Can you just share the question? I think, okay. Assignment questions, I guess it will be better if we discuss next week. Is that okay, Chandrasekhar?
Okay, sir. No
Yeah.
problem.
Oh, yes.
Thank you, sir.
Yes, no issue. One second. Okay. Next, I think we are done with the doubts for today. Yeah, I think we are done with the doubts for today. Wait, is it? No. Siddharth Kapoor.
Hello.
Yes, Siddharth.
Am I audible, sir?
Yes.
Sir, I had a doubt that how do engineers test aircraft components before real world use?
There is a huge process going on then. It will probably take, like, for example, say there's a company coming up with an aircraft. Okay. A new design that they come up with. It will take them easily, 8, 9, 10 years to actually come up with the whole design, test it multiple times, see what is right. They will find a mistake. Go back to the design stage again, run it again. Okay. They'll come back. They'll be like, "Oh no, this is wrong." Will take a long, long, long time. It's not very simple. It's not like making a model and be like, okay, I'll fly it tomorrow. They have to follow all the regulations that particular aviation authority is enforcing, and all such things. It'll probably take around 10, 11 years. Take a long, long time. I hope that was clear. And Vikramasena Pandyan.
Sir, good evening, sir. I have doubt, sir.
Yes.
So we have read that there are two types of engines. One is air breathing engines and the other is rocket engines. Air breathing engines need oxygen as the and it combusts, sir. What happens during heavy weather and rainwater gets inside the engine?
That is the job of an engine. Okay, as you come into this course, such interesting questions will be answered as part of a bachelor's course in propulsion, because there is a lot happening inside an engine. An engine is not just taking air. If there is a rain, it is also taking water molecules into it. So there are multiple filter systems involved. Okay, there are just too many things part of an engine that will avoid all these complications and just take air into the combustion chamber. That's all. I hope
okay, sir.
that was
Thank you,
clear.
sir.
And Aishik Mondal.
Good evening, sir. Can you hear me, sir?
Yes, I can hear you.
Yeah, I have a doubt that in helicopters, there are rotators that play the role of lifting up the vehicle. But in case of aeroplane, how do wings play that same role?
Interesting question. Wait for this week's lecture and you will find the answer. That is part of lecture. I mean, week 2. Interesting set of questions. Yeah, that should get your mind thinking. You will get an answer this week. Don't worry. Part of week 2. And yes, next. I guess we are pretty much done with the questions today. I guess we are done for today. Yep. So see you guys next week. Have fun. Okay, Professor Bharat will be continuing the class next week, most likely. And it's unfortunate that he wasn't able to take part today. He was busy. And yeah, we can meet next week. I hope the class was good. Yeah. You all have fun. Okay. This course is more about, don't worry about the mathematical aspects, guys. It's more about liking aerospace engineering. It's more about see this. Oh yeah, there's a plane flying. Do you understand why it's flying? And at the end of 8 weeks, if you think, okay, this seems cool, can I get into it? And if we have achieved in getting your mindset to that stage, then we are really happy about it. And that's all that we want out of this course. So good evening, guys. Have fun. Okay. I'll be signing off now. Yep. Thank you.